Hello, good afternoon. It's nice to see so many people here. This is my first time at Unite. I'm having a good time so far. The weather's good. I hope you all have a good week. So this talk is about car physics, vehicle physics. So it's a bit more sort of traditional than the previous one. Things with four wheels, more or less. And I'm going to be talking about how you can use Unity's physics system to kind of achieve good, fun car handling and physics. And my name's Bain. I'm based in London. I'm an independent developer. You can find me on Twitter there at oakripes. And yeah, that's about it. So cars are cool. Like, hopefully you agree with me that cars are cool. You probably have some interest in cars or you wouldn't be here. I think cars are cool because they go fast, right? But apart from going fast, how does a car go? A car goes vroom. Vroom, yeah. This is like a really important part to cars. Apart from the speed, especially in video games, because in real life a car can take you somewhere, like to the shops or the school or here. But in a video game, you're not really going anywhere. You're just like making noises, I think. Anyway, so why does a car go vroom? That's like an interesting question to start with, I think. The first part of the kind of car vroom player triangle is the accelerator pedal, or the gas pedal. That's where the player interacts with the car vroom noise. In a video game, the video game I'm making, it starts with a controller and it's on the trigger, right? You might have an actual accelerator pedal if you have one of those steering wheel setups. It might be a button on a screen or some other device. And that triggers air intake. So when you press on the accelerator pedal, it's not kind of opening some valve which pours petrol into the engine. It's actually opening an air valve. And as you may know, anything needs air to burn. It needs oxygen, right? So the more air that comes in to the engine, the more petrol will burn, the more petrol gets sucked in, the faster the engine goes. And this is kind of a takeaway from this is that there's a bit of a delay there. So when you press on the accelerator pedal, there's a fraction of a second whilst the air comes in and more petrol comes in before the engine goes. So in my game, I have a little delay when the player presses the accelerator before that actually takes effect in the force on the wheels. Okay. And the next part in the chain is the petrol burning, which may seem obvious, but actually it kind of explodes, right? And by the time it gets into the engine, it's been heated up and it's petrol vapor. It's like a mist of petrol, which is kind of like flowing through the engine and it explodes. And that explosion that's when the pistons fire. You know, engines have pistons in them, which cause the thing to rotate. And you might have 6 or 8 usually in a car, and each time that piston fires, a bit of petrol explodes, and that makes a noise, right? And now we're getting onto the vroom, right? That's the noise, that explosion. So that happens 3,000 times a second. So 3,000 RPM is kind of like, maybe, I don't want to say average, but that might be what your engine is spinning at. It might be slow, it might be more, depends how fast you're going, what gear you're in, etc. But 3,000 is like a number which is realistic. Yeah, and I did some calculations. So if your engine is spinning at 3,000 RPM, and you've got a V6 engine with 6 pistons in, that means 3 of those pistons are firing for every revolution. So you've got 9,000 explosions a second, which is 9,000 explosions per minute rather, which is 150 per second. And if you're into music, you might know that middle C is 260 hertz, which is 260 times a second it oscillates, roughly, which makes our hypothetical engine, it would be a low D note, right? And when you hear the engine noise, the vroom, going through those different pitches, and often if you're doing audio for an engine, you'll pitch shift it, right? And that's where that comes from. It's the number of times your pistons are firing. And that, maps into the physics of the sound wave, which is kind of cool to think about. The last part of the vroom noise is the exhaust, which is like a big reverb pipe thing. And that's why kind of kids with cheap cars might get big exhaust pipes, because it makes it sound better, right? So that's very important for the vroom as well. Vroom, and now we've reached the vroom. So this is the part where everything goes wrong. There's going to be a short live demo to demonstrate how this can be put to use. So there's going to be some audio here. All right. So what I've done in this little demo is I've taken a explosion sound effect. Try that again. So that's the explosion sound effect, the full long one. And then I cropped it down a bit. I'll play the short one just so you can hear. Is that? Nope. So that's the basic kind of sound effect I'm using. And then if we go into the demo, we should be able to hear something, hopefully. Okay, it's a bit quiet. So that's an 80 RPM repetition of that explosion sound. It's been adjusted by volume and timing a little bit to vary it up so it doesn't sound too artificial. That doesn't really sound like an engine, right? It just sounds like a weird kind of, I don't know, drum circle or something. If we make it a bit faster, it starts to sound a bit more like an idling engine maybe. There's this regular thing which is going on. And a bit faster still, that sounds a bit more like an engine, like it's not quite started yet. So what I've done is I've linked this up to the trigger on the pad so you can get some kind of real-time feedback as that increases up to like this kind of around 1,000 RPM, which might be just as you're starting to accelerate. And that's kind of how you make the vroom noise, with lots of little explosions. Cool. Right, but wheel colliders, that's what you're here for, right? Not weird engine explosion sort of explanations. So basic wheel collider skills. There's like 3 kind of important things that go into them if you haven't looked at them at all. The 3 inputs, you kind of have motor torque, brake torque, and steer angle. And motor torque and brake torque are kind of similar. They have half of that is the same, right, the torque part. And if you don't know about torque, it's a rotational force. So motor torque is going to drive your wheel forwards. Brake torque is going to stop it from rotating. It's going to brake. And steer angle is going to change the direction it's facing. And that's important. With wheel colliders, you don't want to rotate them yourself. You want to use the steer angle to rotate the collider. And wheel colliders compared to normal colliders, it's mainly a list of things you shouldn't do, really, a list of don'ts. So they don't care about physics materials. They don't react in the same way as other things to friction on physics materials. So if you want to simulate some icy ground or some muddy ground or something like that, you need to kind of have some other mechanism to do that. And you can adjust properties on the wheel colliders to achieve some different effects like that, but you have to kind of monitor where the car is, what surface it's on, all of that yourself. You don't attach a rigid body directly. You have to attach it as children, but you're not going to have, like you often do with colliders, a rigid body with a collider on the same object. You're going to have your wheel colliders as children underneath some sort of chassis or something. And like I was saying before, about rotating them with the steer angle, you don't rotate them round either, obviously. You apply those torque forces, and you shouldn't really apply forces to them at all, apart from those torque forces and the steer angle. So yeah, gears. Gears are important in cars. Most cars have got gears. The cars that don't have gears, I know go-karts maybe, or a milk float or something like that, you maybe don't want to have that in your game. Usually, players kind of expect them, even if they're not going to be changing them. There's some sort of expectation there in terms of effects. So this is a graph showing a kind of I think this is from a Chevy Corvette or something. the gear ratios in that car. The first gear is the biggest one, and they go down, you can see. And then the last one is the differential, which is more like another gear, but it's not one you change into, it's just one that affects all of the other gears. So these can be thought of as like multipliers. And they work with the RPM like a proper gear does, but they also multiply the force. So you don't necessarily have to think in RPMs to use gears, you can just think in terms of forces. So you can have an engine force, you can multiply that up to get your first gear kind of force, or multiply it down to get your sixth gear force. And part of the reason this is useful is if you just had a single force acting on your engine, if you had that motor torque static the whole time, you'd find that in order to get going, you need to have quite high force. But if you put that higher force into your car, by the time it's at top speed, it's going to be really going way too fast. It's going to seem unrealistic. Or it's going to take a long time to get going before it gets to its top speed. You want this kind of curve, and that's what people expect when they drive a car. They expect it to top out, the acceleration to kind of like go down over time. And this is another graph showing the same gear ratios, but this time they have what they call the power output over the gear. So each of them, and you can see it most with the first gear, the yellow one at the top, has got this big kind of upside down U shape. And they all have that, but some of them are more stretched out. And down the bottom, you've got the engine, which is the black line. And again, you can see that curve going down, and that's the power into your engine. The torque is up the side, is going to go down over time as the car goes faster. But in between each gear, it's going to kind of start slow, go up a bit, and then go back down again. And that, you may not need to go into as much detail as that, but for example, if you think about that classic car noise that, you know, if you hear a Formula One car going around a track and it's going, nah, 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 you know, that creeping sort of acceleration kind of noise. That's what's happening here is the speed is going up, but then it's getting cut off back down to the next gear. And each time it starts in a new gear, the speed and the power output is low, so it's going to climb back up a bit before dropping down. So it's kind of like a stepped acceleration curve when you kind of add those in together. Okay, the engine. So we've kind of talked about engines a lot, I suppose. I've been talking about how it works inside the engine. But often that stuff is interesting to know, but maybe not so interesting for your player. I mean, they're not going to see the inside of the engine. They're not going to see all the mechanisms or the petrol or the explosions or anything like that. They might hear it, which I've talked about a bit, and they might see some indication of that, an RPM counter or something. So you can try to work out, you know, the speed of your engine. You know, use your gears to work out how much force that would result in, and then apply that force to the wheels. I found that it's easier really to work in reverse, to have some kind of base force for your engine, use some gearing system to work out what force that would translate to, and that's just a multiplier onto your wheels. But then you can get the wheel speed from the colliders, so you can get the RPM for the wheels. You can work that back through your gear system to work out what the RPM then should be for your engine. And then you don't have to worry about all the internals of the engine. It's all a bit simpler. And you can use the engine RPM then if you have it, as well as for sound effects or for like an HUD, to change gears. You know, if the RPM is getting up high, like 6,000, 10,000, then you can change down to change up to a higher gear, or if it's going too low, you can change down to a lower gear. And you can use it for wicked sick sound effects. Okay, friction. Slip curves are a term you'll come across, and I'm going to try and explain them to you in a few minutes. But they are what Unity uses to represent friction for wheel colliders. So you don't just put like a single friction value like you might on a normal box or something. You have these things called slip curves. And the first thing to know about them is that they work in two separate directions. So you have a forward and back slip curve, and you have a sideways one. So the friction that the tire or the wheel is going to have moving forward on the ground is going to be different to the one, or it can be different. You can set the values to the same if you like, different to the sideways one. And that's kind of important if you want to think about acceleration, hill climbing, or like doing drifts, or doing skids, handbrake turns, And what the hell is this? So if you start looking into wheel colliders, it won't be long before you come across this graph, right? It's like force, extremum, I don't know what that word means, slip, stiffness, all these kind of weird concepts. And it's quite confusing. It's quite a confusing way to model friction, but it turns out to be quite an accurate way, I suppose. So this is what's known as the slip curve. And it's kind of confusing because when you first look at this, you might think, oh, I want my car to be more grippy, right? I want it to have more traction. But what are the inputs to this curve? Like, and what are the outputs? Force, you might think that's the input, right? You're going to put force into the wheel. So maybe you put force into this equation and you get out how much the tires are slipping. But that doesn't really make sense because force is on the wrong axis. Unity lets you change the extremum and asymptote points to affect the shape of the curve, so you can make it taller or shorter. You can make the peak come later, and you can make that asymptote higher up. And I think the key to this is the term slip. I'm not sure where this originates from, although I have some theories. But it's kind of a weird name. And when you hear it, you think like wheel spin, right? You think something's slipping. It's losing traction. But I think it's better to think about slip in this sense as more like something being wound up. And this is how I want to explain it. So you see this picture. It shows how tires are squishy, right? And when the axle moves, the tire doesn't move exactly the same. There's some delay between the movement of the axle, the engine, and the movement of the tire on the road, and therefore the movement of the car. And the slip value is kind of like the amount that the tire is wound up. It goes from 0 to 1. Well, it can go down to -1 as well. But for 0, the tire is completely straight. At 1, the tire is wound up just like that, as much as it can be. And then at that point, it's going to start spinning, right? Because the tension in the tire is too much, and it has to be released, and the wheel's going to spin. So in this graph, at the beginning here, down at 0, is when you're not moving, or if the car's going at a constant speed, it could be there too. As you start to accelerate, that tire gets wound up like a spring a bit more until that extremum point is when the tire is most efficient, and it's putting out as much energy as it can, but it's still wound up, like it's not getting unwound. And as you move down to the asymptote, that's when the tire is spinning, and it's moving too fast for relative to the ground underneath, and it's losing energy then, so it's not as efficient. So if you wanted to make your car more grippy, you can move this asymptote up so that more force is output even when the slip value gets very high, when the tire gets really wound up. And this is the magic formula. This is kind of where slip curves come from. And it's called magic formula because it's not really based on physical properties, right? It happens to fit them. Like it happens to simulate a car tire very well, but it's not derived from some kind of property of rubber or something like that. And we have to thank for this kind of lovely, confusing formula, which will have you tearing your hair out. We have a Dutch man called Hans Paceja. I'm probably going to pronounce that wrong. Pacejka, but we're in Amsterdam and he's Dutch, so I thought that was interesting. Okay, so this last part, I'm going to talk about some sort of practical advice. So how do we solve problems? You can drink our way through problems, but they don't go away. They just get worse. So perhaps we can try some bullet points. As I was saying, one problem I had with my game was my cars couldn't climb up hills, and it was there was a lot of off-roading in the game, so that was a bit of a problem. If you just increase the power of the wheel torque, the wheels will spin. So you can take the forward friction, which is the forward value, increase that asymptote. So rather than the curve dipping down at the end, it just looks like just goes right to the top, and increase the engine torque at the same time. You can increase the asymptote values up above 1, although that's kind of unrealistic, but it may work. And I've got a little, I've got a little video, I think we've got time yet, just to show you the difference that can make. So hopefully this works. There's no sound on these. But this is the default car I had. So it's the one that the camera's tracking sort of in the middle there, and it's just falling. This is like a plane with a 20-degree incline. It's just falling right back down. And you'll see in this this setup I've got kind of dozens of cars, all with slightly different values, as I was testing out all the different, the different values and trying to get the right ones. And this was the sort of winner, if you like. So he does a lot better. Look at him go up the hill. He's winning. Yeah. So it can make a big difference. And obviously that's going to make a big difference to the handling and the feel, as well as the practical things. Like if you've got hills in your game, the car needs to be able to go up them. How to stop wheel spin. So this is kind of related to the traction thing, but it's not quite the same. So in that example, when I increased the asymptote value and the engine torque, I still had a fair amount of wheel spin, which can be okay, but it might not be what you want. If you have sound effects which are linked to that, and tire squeals or dust particles flying off, then that's going to be thrown out if the wheel spin values are all wrong too. And the key thing I found to think about here is that players don't accelerate like real drivers. They don't drive like real drivers, except perhaps in some very high-end simulations. They generally don't. If you're driving a car, you're not going to sit behind you don't slam down the gas pedal right to the floor right from the get-go. If you're using a controller, generally you will pull the trigger right down as far as it will go, or pretty close. And that's kind of the reason, in a way, the physics is just simulating what would happen if you do that. The wheels are going to spin, right? So you can use traction control here. If you don't know, if you haven't heard of traction control before, this is like a concept they have in real cars, often in like off-road cars, where if a wheel doesn't have as much grip on the road, it's going to get more power. It's going to get less power, from the engine, and vice versa. So usually that helps, like if you're going around a corner or going over some muddy terrain, so that the wheels with traction will get the power and move the car forward, stop it from getting stuck. But in this case, you can use the same principle to account for the player accelerating too fast, right? If the wheels start to spin, you can limit the power that's going to them and bring that down to a more reasonable level. As the car starts moving faster and more power is suitable, then you can ramp that up again. And the Unity Wheel Collider demo car has traction control in, which it's a very reasonable implementation there, so you can have a look at that. But it may be confusing when you look at it and think, why do I need traction control? That seems like a fancy feature or something. It's not necessary, but that's one of the main benefits of it. And then the next one is spinning out, and this is kind of a problem I had quite a lot with my game. So let me show you a quick video of what I mean by spinning out. So there's a bit of judder on this demo, so ignore that. But if you watch the car, this is another demo I set up where the car's driving. When it gets to a certain speed, it's going to start turning. In that case, it starts turning, it does a complete 180. And obviously you ignore the big planks on the wheels. That's to kind of so I can tell if they're spinning or not. And that can be a big problem. And I found that when players would play, they tried to take a corner, and suddenly the whole thing would do a 180. And it's very annoying because then they're sort of stuck. And it may seem obvious to state this, but it happens with the back wheels overtake the front wheels. So front wheel drive helps a lot. Now I thought, oh, I want rear wheel drive like a big American sports car. That's the cool way to drive a car. But actually, I've never driven a rear wheel drive car, and a front wheel drive car is a lot easier to control, and it's kind of actually what turned out I expected in the game. I also found that you can, if I decrease the side friction of the front wheels, that would help as well, because then they wouldn't kind of get jammed, you know, it let them move a bit when they were turning too much. You can also try to adjust the center of mass, so you can move that back a bit, which will take some of the weight off the front wheels and stop them again getting dug in, but that can reduce the drive, the acceleration. And the last one, reducing steering at high speeds. That kind of comes back to what I was saying about how players don't drive like real cars. They don't drive games like they do real cars. So again, if you're moving slowly in a car, you're going to turn the wheel probably quite a lot, you know, if you're parking or something, versus if you're driving along a motorway, you're going to be moving it quite a small amount. Whereas in a game with a thumbstick or whatever input you have, generally it's going to be the same. You know, the players are going to put it at full whack regardless of the speed. So you can again have something to limit that. You know, measure the speed of the car and taper off the steering so that when they're going fast, that the thumbstick has less effect, or the control has less effect on the steering. Okay, and the last part is tips for tuning your cars. Oh, I was going to show you the, actually we're running out of time, I was going to show you a quick video of the better steering. So this is with some of those tips in mind. Again, try and ignore the judder. For this car, doesn't look like much, but you know, it's exactly the same speed, turning angle, but now it's not spinning out, right? It's just going round in circles. Okay. So yeah, these are some little screenshots of my, you know, properties on the car, and there's probably even more now, but the point is not to show you that those are good ones to have, but to show you that there's lots, right? And if you start trying to just like pick any one and change it a bit, it's going to be really hard to see what actions have effect, and you know where you want to, what you need to change and what changes are working and everything. So the approach that I had, and it's kind of what I've shown in the last few points, is to pick different problems to solve. So identify the fact that your car can't go up a hill, or that the acceleration is too slow, or that when it turns it tends to spin out, and try and fix one of those. So in my examples, I took those ideas and I wrote a little script to drive the car up the hill without me having to play it, or go to a certain speed and turn a corner. And then I would take that car and duplicate it and change one thing and then see how that works, and then duplicate it again, change something else. And you can see I've got you know, all these different silly, strange names for my cars, like high slip, asymptote, high engine power, and high slip, and it goes on. Everything is just changing one single thing to see what the effect of that is. And keeping the old ones around so you can kind of, because my memory is terrible, and I would think, oh, the old one was better, but then I would look at it, and it turns out it wasn't, or it was. Right. So, yeah, so just to summarize, Joe's best tips. Traction control may seem unimportant, but actually it does affect handling a lot, and particularly with wheel spin. To get RPM values for the engine, it's best to work backwards from the wheels. You can get the wheel RPM through the wheel colliders. Unity does that for you, and it's very easy to get the RPM backwards from that. For those friction values, you can use a thing called stiffness, which is basically a multiplier of the whole thing. That's a very easy way to vary handling, so you know, if you're going over a slippery patch of ice or something. Number 4, center of mass affects handling a lot. And so that can be a good way to vary car models in your game. Say you've got a basic car which works pretty well, you want to have a few different variations on that to keep players interested. Moving the center of mass up or down or backwards or forwards will really affect how it handles. So, and it's quite easy to mess around with that, right? And the last one is pick problems that you want to solve and iterate on them. Don't get stuck into the thing of going, oh, the car's not quite right, I'm just going to tweak this and tweak that and tweak another thing. You have to be kind of a bit focused sometimes in order to get the best out of the physics system. Okay, so I've got a few references there. I'm sure you won't read those, but I'll put these slides up online. Hopefully there's somewhere I can post them on the Unity website, or if not, you can find me on Twitter. It was Oakripes. Yeah, thank you very much for listening. We might have time for a couple of questions. Thank you.
Are there any questions?
Yeah. How would you determine which wheel is on what kind of surface? Like if you're driving a car on a road and 2 wheels are on the grass, how would you determine on which surface they are, and how would you react to that?
Yeah, that's a good question. So I would probably, I have on my car lots of other colliders on the chassis, and you can have not colliders which are just triggers, right? So I would probably use those to tell where the car is, what kind of surface it's on. Yeah. Well, so you can place trigger. You can place some like box triggers over the wheels just to get a rough idea. Yeah.
Any other questions? At the back here. That will be our final question.
Thank you. So, hello. Just a very quick one. If I want to make a game with, letting the car to jump or everything else, does this system work? So do we need to tweak, like, if you know what I mean, to not let the car to looks like in a movie in which they fly or stuff like that?
No, it works. It works pretty well. I think I've got jumps in my game. One thing is that when you do a jump, the wheels will spin freely, so the engine will suddenly rev a lot. You might want to cut the accelerator or something at that point. But yeah, it works fine in the air as well.